Welcome to today's lecture. So we're going to continue lines, then we're going to start talking about planes. Well, what we learned so far? Review. We learned about different equations of a line in the space. A line in the space. We define the vector equation this way. We say that A R is equal to R sub 0 plus T V. And we call V the direction vector. So this is the vector equation. Then we use our vector equation to define parametric equation of a line. The parametric equation of a line is written this way. X equals to X sub 0 plus AT, Y is equal to Y sub 0 plus BT, and Z is equal to Z sub 0 plus CT. Parametric equation. Then we use parametric equation to write symmetric equation of a line. X minus X sub 0 divided by A is equal to Y minus Y sub 0 divided by B equals to Z minus Z sub 0 divided by C, which is called the symmetric equation. So these are the equations of a line in the space. If we have a line segment, the equation of line segment is written this way. The equation of a line segment between R sub 0 and R sub 1 is written as R of T is equal to 1 minus T R sub 0 plus T times R sub. So here you have just a line segment, a segment of a line. And T is bounded between 0 and 1. So our goal is to analyze lines in the space. We started by defining points, then we defined lines. Now, we want to know what is the relation between two or more lines in the space. This is our goal. How to analyze lines in the space. First of all, recall that in algebra, we have two lines like L1 and L2. L1 with slope M1, L2 with slope M2. We say that L1 and L2 are parallel to each other. L1 is parallel to L2 if M1 is equal to M2, if they have the same slope. How about 3D? So this is in 2D. How about in the space? When we say two lines are parallel to each other, what's the relation between the direction vector of L1 and L2? So in 3D, two lines are parallel if their direction vector are parallel to each other. again, in algebra, we learned about intersecting lines, perpendicular lines, or in general, intersecting lines. So in 2D, we say that two lines are intersecting if they have L1 and L2, if they have a point of intersection. We can, by solving equations of the lines, we can find the point of intersection between them, A and B. Point of intersection. By solving for X and Y, we can find the point of intersection. How about 3D? 3D follows the same pattern. We say that two lines are intersecting. It means that if we solve the equation for X, Y, and Z, remember that in 3D, we are working with three coordinates, X, Y, and Z. We can find the point of intersection between two lines. So in this case, your point of intersection has the third coordinate, Z, as well. Intersecting lines. So now in 3D, we are talking about another relation between two lines. We call them skew lines. If two lines are not parallel to each other, they are not intersecting, then we call them skew lines. Two lines are not parallel nor intersecting, we have skew lines. How do we visualize them? So two lines are parallel to each other, parallel lines. Intersecting lines, skew lines, they are not parallel to each other, they are not intersecting. So we have skew lines in this case. Example says, analyze these two lines. The first line is given to us as L1, X is equal to 1 plus T. Y is given to us as -2 plus 3T. And Z is given to us as, well, 4 minus T. Then L2, the second line in parametric form, is given to us as X equals to 2S. Guys, we're using a different parameter to be able to distinguish between these two lines. So the parameter for the first line is T. The parameter for the second line is S. Y is equal to 3 plus S, and Z is given to us as -3 plus 4S. Well, okay, we have two lines. Are they parallel to each other? Let's check to see if they are parallel. So we need to find the direction vector of these two lines, if there is a connection between them, if they are multiples of each other, if they are equal to each other, we say that, hey, they have parallel lines. The direction vector of L1. This is V1 equals to 1 3, and minus. So the coefficient of t, which is 1, the coefficient of t, which is 3, and the coefficient of t here is -1 times t. So V1, or the direction vector of L1. Now the direction vector of the second line of L2 is going to be 2, 1, and 4. 2, 1, and 4. What is V2? So what's the relation between these two vectors? Are they equal to each other? No. The first coordinates, the first component, the second component, and the third component are different from each other. So V1 is not the same as V2. They are not the same. Do we have them as multiples of each other? It means that if I divide the components, I need to be able to get to one constant. So let's do that. 1 divided by 2, 3 divided by 1, -1/4. So as you can see, you don't get to the same multiples or components. There is no relation between V1 and V2. No relation between V1 and V2. So it means that they are not parallel to each other. Are they intersecting? Intersecting. Okay. How do we analyze intersection between two lines? Remember that if you have just two lines in the plane, just here, two lines in the plane, it's easy. You only have x and y. You can form system of linear equations, solve for x or solve for y, use that value in one of the equations and find the second missing variable. To find the intersection between these two lines, we need to start by taking two equations and solve for s, t. So form a system of linear equations to solve for s and t. It doesn't matter if you're using x, y, or z. As long as you have two equations, you're done with solving s, t. So for simplicity, let us take xy and xy. 1 plus t is equal to 2s. -2 plus 3t is equal to 3 plus s. So from algebra, we know that t is 2s minus 1. We substitute it here. We get -2 plus 3s equals to, this is s, this is t. 3 times t, which is 2s minus 1 equals to 3 plus s. And we start solving for s. We get -2 plus 6s minus 3 equals to 3 plus s. So 5s is equal to 8, or s is 8/5. Now you can plug that back into the equation between t and s and solve for t. So t is equal to 2 times 16/5 minus 1, which is 11/5. This is our t. So we used x and y. We used x and y to find s and t. Now we need to find z. So z, let's write this on here. Z is equal to 4 minus t. My t is 11 over 5. So I get 9 over 5. This is my z. What if I plug in s here? If I plug in s here, my z is equal to -3 plus 4 times s. So my z is equal to -3 plus 32 over 5, or 32 minus 15 over 5, or my z is equal to 17 over 5. Okay, what is wrong? What is wrong? You got two different z values. If the point of intersection is here, it must have the same, exact same x, y, and z. I found s, I found t, and it gives me a different z value. What's the meaning of that? It means that they are not intersecting. They are not parallel to each other. They are not intersecting. So we have skew lines. These two lines are skew lines. So far we talked about lines. Now we're going to move on to talk about planes. Planes in this sense. Well, to write the equation of a plane in the space, we always start by having a point. So to write equation of a plane that passes through the point p sub 0, x sub 0, y sub 0, z sub 0, we need a normal vector which is perpendicular to the plane, including that point. We need a normal vector denoted by n. So since it's a vector, it has some components, a, b, and c. Then the equation can be written as a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 equal to 0. A, x sub 0, these are numbers. B, y sub 0, these are numbers. C, z sub 0, these are all numbers. So where does it come from? So suppose you have a point p sub 0 in this sense. They have a plane passes through this point. This is your point. Plane P. since this is a plane, it passes through many points. Let us take another point like P sub 1 with coordinates x, y, and z, and actually construct a vector in the plane. This is your vector in the plane. So this vector passes through these 2 points. So this vector can be written as P sub 0, P sub 1 with a bar on top of it. We also need a normal vector, a vector that is perpendicular to the plane. So this is a normal vector perpendicular to the plane A, B, C. Since the angle between these 2 vectors is 90 degrees, it means that the dot product between these 2 is equal to 0. So you can write since P sub 0, P1 is perpendicular to normal vector n, it means that their dot product is 0. Okay, let us construct the dot product. Here we have A, B, C, dot product with a vector passes through these 2, x minus x sub 0, y minus y sub 0, z minus z sub 0 equal to 0. So the definition of dot product, we just multiply the first component plus you multiply the second components plus you multiply the third components, and it is, since they are perpendicular to each other, it is 0. So A times x minus x sub 0 plus B times y minus y sub 0 plus C times z minus z sub 0 is equal to 0. That's how we get the equation of a plane passes through a point like P sub 0 with normal vector. Okay, our example says write the equation of a plane that passes through the point 2 or minus 1, and the normal vector is given as n is given as 2, 3, 4. Perfect. So the equation of the plane can be written as A times x minus x sub 0 plus B times y minus y sub 0 plus C times z minus z sub 0 equal to 0. Let us identify the information that are given to us, then plug them in and simplify and eventually graph our plane. This is our point, x sub 0, y sub 0, z sub 0. This is our normal vector, A, B, and C. Well, we have 2 times x minus 2 plus 3 times y minus 4 plus C is 4 times z plus 1 equal to 0. We don't leave it like this. We distribute the coefficients and we try to simplify. Simplify. 2x minus 4 plus 3y minus 12 plus 4z plus 4 is 0. Okay, so here you can cancel out negative 4 and 4. You get 2x plus 3y plus 4z equals to 12. So if we simplify the equation, we get ax plus by plus cz equals to d. This is okay. To graph this, you're going to find x-intercept, y-intercept, and z-intercept. To graph, find the x-intercept. To find x-intercept, we said y and z equal to 0. So here you get 2x plus 0 is 12, so x is 6. So the point of intersection with x-axis is 6, 0, and 0. Now find your y-intercept. To find y-intercept, we said x and z equal to 0. So we have 3y equals to 12, or y is equal to 4. We get 0, 4, and 0. This is 0. And finally, let us find z-intercept. Find z-intercept. To find the z-intercept, we set x and y equal to 0. So we get 4z equals to 12, or z is 3, 0, 0, and 3 is your z-intercept. Okay. X-axis, y-axis, and z-axis. Our x-intercept is 6, 0, 0. Our y-intercept, 0, 4, 0. And our z-intercept is 0, 0, 3. So our graph intersects with x-axis, y-axis, and z-axis, and partially you can visualize it this way. Note that your plane continues on all sides. We're just looking at this partially to understand the behavior of this plane. Again, it continues on all sides. Well, let us take a look at our online calculator to visualize this. Let us add an object, implicit surface. So we're trying to graph this plane. We have 2x plus 3y plus 4z equals to 12. So we can visualize this plane partially in the space. If we change the limit of x, of y, of z, we can see the expansion of this plane in the space. So again, for simplicity, we try to restrict these boundaries to understand the behavior of the plane. But in general, your plane in the space continues from all sides. So this is the link that we're using.